We are on Unit 6, Notes 5, and today we're going to take a look at something that's called Euler's Method. Euler's Method. So I'd like to begin just by introducing this to you, what it does, before we go to your printed notes. Euler is named for Leonhard Euler. He was a Swiss mathematician back in the 1700s, and he did numerous things in math, physics, astronomy. Anyway, big guy, Leonhard Euler. He is the one who named E. He's the E that we have, E. It's named for Euler. Okay. Anyway, Euler's method, what it does. First of all, you need to know what it does. Euler's method approximates the value of a function. So that means it approximates the y value, all right, if you're graphing it, the y value of a function, okay? So that's what it does. And you might think, why would we need to approximate the value of a function? Because so many times we have a function and we have some kind of equation for a function, and why do we need to approximate the value? Because we can put any number we want in for x and get the value. So why do we need to approximate the value? Well, in these types of problems, the reason that it becomes important to know how to approximate the value is, what if we don't have an equation like this for a function? What if that's not available to us? What if all we have is a differential equation that we don't know how to solve, or we don't know how to solve yet? Like this one. I brought this up at the very end of Notes 4 last time. I brought this up and I said, well, we don't know how to solve this yet. There's a course in college called Differential Equations where you'll learn to solve it, but right now we don't know how to solve this. And there are other differential equations that we cannot solve at all. All right. So Euler's method, or it's just very tedious to solve. So Euler's method provides a way to find something about what the function is equal to. Okay? Even though we can't solve it, we can still find values of that function. Okay? Tomorrow, what we're going to be doing is we're going to be able to take a differential equation that we cannot solve, and even though we cannot solve it, we'll be able to graph it, find a picture of it. So really cool stuff here for differential equations that we cannot solve. All right? So here is graphically what Euler's method does. Let's say that we have a point. We know a point. So you're going to be given a point. Okay? Let's call it xy. Okay? Given a point. And you're going to be given an equation for, or you're going to be given information about the derivative. And remember, derivative is slope. So the dy dx gives us the slope of the curve at a point, right? So let's say that this point that we were given is the point 1, 2. Let me change that to 1, 2. Then here, the slope, if this was our slope, the slope at that point would be 3, right? So we know the slope is 3. Kind of steep, right? So what if we didn't know what the curve was doing, but we wanted to know what f of 1.5 was? Well then, even though we don't know exactly what it is, we can approximate f of 1.5 by using the slope. We know f of 1.5 wouldn't be down here, right? Not very likely down there. And so this gives us a way to approximate the slope. Okay, now, what if we take this one step further? What if we have a point that we're given? Let's keep that 1, 2, I like that. Okay, and let's go ahead and keep our dy dx. Okay, so we know that the slope right here, the slope is 3. The slope is 3. Okay, so we can use that to approximate, let's say, x equals 1.5. We can use it to approximate that point. Okay, then we find the slope at this point. That point, let's say the slope there is a little bit less. Let's see, it's like that. Then we can use that to approximate that point. Maybe x is equal to 2. So now we have an approximation for x is equal to 2 using the slope here and the slope there. Maybe we find the slope here. Maybe that slope is a little bit flatter. Well, we can use that slope to approximate maybe x equals 2.5, right? So we're using the slope at the previous point to find the point here. This is what Euler's method does. Okay? We're using a point and the slope to get a value, and then using that point and a new slope to get another value, and so forth. We can do this as many times as we want. So that's in a picture, that's what's going on. Now let's go to your printed notes. Okay? All right. So know what Euler's method does. It approximates a point. It approximates the value of a function. Okay? When you think of Euler's method, I would like you to think of the point-slope form of the equation of a line. So think of this, point-slope. We've been using this all year long so far, right? So it's old hat by now, right? M is the slope, and you will be given information about the slope in the form of dy dx. Okay? X minus x naught here, this is going to be the change in x, right? This is also the change in y, but this change in x will be the same throughout each problem. So this is the same each problem. In fact, the first thing I always do is find my dy dx. All right, let's take a look at how we do this. First of all, we're given this differential equation. They give us the differential equation. Now this differential equation we could actually solve, right? Because it is separable. There's only x's there. But we're going to use this and we're going to do an Euler's method on it. So they gave us the differential equation, which is the slope. Remember, that's our slope. And they gave us an initial point. 0, 5 is our initial point. Okay? So let's get going. First of all, it says find an approximation for y at point 8 by using Euler's method with 2 equal steps. So first thing I want you to do is find delta x. Find this change in x. Okay? So we are going from x equals 0 to x equals 0.8 in 2 equal steps. So delta x must equal 0.4. Has to. So in this problem, delta x will always be 0.4. So this will always be 0.4. Okay. Next thing I want to do, because I want to use this, so I found delta x, now I need to find my first slope. So my first slope at my given point. This is at the given point. So I would plug in 0 for x and 5 for y if there was a y over here. So this will just be 0 minus 2, which is negative 2. So my first slope is negative 2. Okay? Let's use the equation of the line to find that y value. We're finding that first y value. Okay? So y minus the y value, 5, is equal to our slope we just found times x minus the x value, but remember that is delta x, and that always stays the same throughout this whole problem. So 0.4. Now we can find y. So y will be 5 minus 2 times 0.4 is 0.8. So our first y value at the middle x value, so y at 0.4 will be approximately 5 minus 0.8, which is 4.2. Okay? So that's our first point. Now let's go find our second point. Now we're using this point. So we know delta x, we need to find the slope at that point. So the slope at 0.4, 4.2, will be 0.4 minus 2. And 0.4 minus 2 is negative 1.6. Had to think about that. Okay. Usually we do not have a calculator for Euler's method problems. Okay. So now, equation of a line. Y minus the y value is equal to our slope times x minus the x value, but remember that's always delta x in the problem, so 0.4. Okay, so y will equal 4.2 minus, okay, I know what 16 times 4 is, that's 64, so it's going to be a 64 with 2 decimal places, so 0.64. Right? So our answer, y at 0.8, is approximately 4.2 minus 0.64. Without a calculator, this is how I got to do it. This will be 10 minus 4 is 6, but I borrowed from here, so 11 minus 6 is 5, and 3 minus 0 is 3. So I believe that's negative 3.56. Okay? So we approximated a y value, we approximated a function value. Okay? Using 2 steps. So think about that point. This was our initial point, 0, 5. We found the slope to be a negative 2. So we used that slope to get this new y value, and this was our new point. We found that slope to be a negative 1.6. So then we got our new y value there. Okay? All right. Part B here. Let's solve the differential equation. Given our same initial condition, and use our solution to find the exact value. So in part B, we're seeing how close were we with this Euler's method. How close were we? So let's solve this differential equation. It's not going to be too hard. Separate. So taking the integral of each side, and we have y is equal to 1/2 x squared minus 2x plus c, right? Let's find c. So we're putting in the 0.5. So 5 will equal c. So y is equal to 1/2 0 squared minus 2 times, I'm sorry, I just did that. Y is equal to 1/2 x squared minus 2x plus 5. Okay? So there's our y equals. Now we can find any point that we want, right? So y at point 8 will be 1/2 of 0.8 squared minus 2 times 0.8 plus 5. And I cheated and I did use my calculator for this one, and I got 3.72. Okay? So, I'm sorry, negative. No. Goodness, this was positive up here. This is the time when in class, good grief, that was a positive. That was like when in class somebody would say, Miss Murray, that's positive. And I'd say, oh yeah, you're absolutely right. So that was positive. Okay, anyway. All right. So anyway, our approximation using 2 Euler's method steps was not too far off. How could we have gotten closer using more steps? Okay, if we had used more steps, we would have got closer to the 3.72. Okay. All right. Example 2. Given this differential equation, this was our x plus y here. Given dy dx equals x plus y, let y equals f of x be the particular solution to the given differential equation with initial condition f of 4 is -1. So let that be. We can't find it, but just let it be. Let it be. All right, use Euler's method starting at x equals 4 with 2 steps of equal size to approximate f of 4.2. So step 1, I always find delta x. So what is delta x here? We're going from x equals 4 to x equals 4.2 in 2 steps of equal size. So delta x has to be 0.1. Okay? All right, first dy dx. So we start at our initial point. So dy dx will be 4 minus 1, which is 3. Okay? Y minus the y value is equal to our slope we just found times delta x. X minus the x value. That's what delta x is. So y will be -1 plus 3 times 0.1. This is when I might be tempted to go to fractions. I prefer fractions to decimals, clearly, after I butchered that last one. Anyway, this is 0.3. 3/10. So our first stopping point here, f at, we went from x equals 4 and we added 0.1 to it. So 4.1 is approximately -1 plus 0.3 is -0.7. Now we use that point to find our next slope. Okay? So I'm plugging in 4.1 for x and -0.7 in for y. Here we go again with subtracting decimals. But anyway, 11 minus 7 is 4. Okay, 3 minus 0 is 3, and that is a positive 3.4. Okay, equation of a line. Y minus the y value is equal to our slope we just found times delta x. So y will equal -0.7 plus 0.34. Okay, this might be a good time to say stop. So f at 4.2 is approximately -0.7 plus 0.34. Okay, this is going to be negative, and it's going to be 3.36. But I would say stop there. Okay? Alright, I hope you guys get this process. It's not hard. And it's the same thing over and over and over. I don't have very, I think I gave you guys 6 problems to do, because I don't think we need overcut in learning this process. Okay, I have one more example for you though, and this is when we have information given in a table. Alright? So assume that f and f prime have the values given in the table. Use Euler's method with, again, 2 equal steps. I use 2 because that's what I see most often on AP exams, okay? To approximate the value of f of 2.6. So we're looking for f at 2.6. Okay? All right, find delta x. So we're going from x equals 3 to x equals 2.6. So what is delta x this time? It's going to be negative because we're going down, negative 0.2, right? Okay? So what is our first slope? What is our first slope? Our first slope is 0.4, right? So I can go, since it's already there for me, I don't have to like write it all out, it's already there. But some people like to write it out. So if you want to write it out, do dy dx at 3, 2 is equal to 0.4. That's fine. But you don't have to because it's sitting there. I'm going to go straight to my y equation. So y minus the y value, 2, is equal to the slope times delta x. So y is equal to 2 minus 0.4 times 0.2. 2 times 4 is 8, and I need 2 decimal places. Okay? So our first stopping point, f at 2.8, is approximately 2 minus 0.08. So that's 1.92, I believe. Okay? So if we wanted to, we could put that right here. It's approximately 1.92. It's not exactly, it's about. Okay? Time to go to our next equation, because now we're using this point and that slope, right? So y minus the y value is equal to the slope times delta x. So y will be 1.92 minus 2 times 7 is 14. With 2 decimal places will be 0.14, right? So f at 2.8 is approximately 12 minus 4 is 8, 8 minus 1 is 7, and I get to keep my 1, so 1.78. 1.78, approximately, not exactly. Okay? One quick thing before I leave you. I want to write this if we had not actually found this out. How do we get there? So I'm going to write this f of 2, that should be 2.6, goodness, 2.6 is approximately equal to, let's see how we got that. How do we get that 1.92? That came from here. How do we get that? That came from here. And 0.08 came from here. So this was 2 minus 0.04 times, well, plus 0.04 times negative 0.2, writing it in that way. That was the 1.92. And then what do we get here? That was we added 0.7 times negative 0.2. If you put all of that into your calculator, you get 1.78. Okay, so I want you to see where this all came from. This was our initial y value. right? Initial y value. This was our first slope, delta x. This was our second slope, delta x. We had the information here to approximate. We could have come and done the next x value as well, huh? Because we had that next slope. So we could have done that. But as we are here in this problem, we did not need that slope at all. Don't use it. Just extra information. Okay? All right. Go practice and see how you do. And this was a short lesson, so you have plenty of time to go and practice. I want to say it's only 6 problems on that worksheet. So I know it's not too much. Okay.